Hey guys, this is Mr. Mitchell. Today we're going to be talking about Newton's law of universal gravitation. So the force of gravity is one of the four fundamental forces we've discussed, and when we sort of introduced that, we said that gravity is an attractive force that draws two masses together, so it pulls two masses together. The gravity depends upon the quantity of those masses and the distance that's between the two masses. What we did not get into is Newton's equation. So Newton actually defined an equation to calculate the actual force of gravity between objects, and this is what he came up with. So Fg stands for force of gravity, G, m1, m2 over r squared. So m1 and m2 are just the masses, okay, so the value of those masses or the quantity of those masses. And then r is the distance between the two. It's the center to center distance, so from the middle of each of those objects. The g value is called the gravitational constant, and since it's a constant, it's always going to be the same for every single problem you ever solve like this, and the value for that constant is 6.67 times 10 to the negative 11th meters cubed per kilogram second squared. We're not going to get hung up on the units there, but suffice to say that 6.67 times 10 to the negative 11th is a really tiny number. So we've just been introduced to this equation. Let's kind of dive right in here and try to solve a problem using it. So Mr. Mitchell's testing gravity. He tosses a 7 kilogram bowling ball into the air, then immediately throws a 1 kilogram tennis ball up next to it. What is the force of gravity between the two if the center to center distance between them is 2 meters? So I toss the bowling ball, immediately toss the tennis ball, and I want to measure gravity between the two while they're up in the air. So as we did in physical science, the first step is always going to be to identify our givens. So we recognize that the bowling ball has a mass of 7, so we write that down, mass 1. Mass 2 is the tennis ball, that's 1 kilogram. And then gravitational constant is always the same value, 6.67 times 10 to the negative 11th. And the radius or distance between the two is defined as 2 meters. Our next step is to identify the equation we're going to use, and we're going to use Newton's equation that we were just introduced to. And so we write that down. And then the work and solution section, we're going to just plug and chug. We take those values we've written down from the problem, and we put them into the equation and solve it. So we'll start with the gravitational constant, multiply by the mass of the bowling ball, the mass of the tennis ball, and then divide by the distance between them squared. When you do this all out, you get this value, 1.17 times 10 to the negative 10th newtons, because force is measured in newtons. And I've also expanded it out here for you so you can see just really how small the value is. Okay, and so we mentioned previously that the gravitational force is the weakest of the four fundamental forces, and here's some quantitative evidence to demonstrate that. As a comparison to show you just how small it is, because perhaps you're not able to contextualize newtons as a measurement of force because you're used to measuring force in pounds. A field mouse, little old field mouse, has a weight of 0.189 newtons on average. And so a field mouse has a larger weight, a larger force pulling it down to the earth than these two balls experience from the force of gravity between them. And in fact, it's actually an order of magnitude of 10 as a difference between the two. So gravity is a really tiny force, and it's largely because of this really tiny constant we always have to multiply by. And so, as we mentioned in class, right, in order for gravity to be significant, we have to have these enormous masses to multiply by in order to help us overcome that really small constant. I want to do a quick couple notes here on proportion because we want to be able to look in science at equations and analyze whether things are directly or inversely proportional and what might happen to different variables. So this is Newton's equation again. I want you to think for a moment about whether you think the relationship between the force of gravity and the mass, it doesn't matter mass 1 or mass 2, is that relationship directly or inversely proportional? So what I'm hoping you recognize is that they're directly proportional because as the masses increase, then we'd think that the force of gravity should increase, and that's maybe just an intuitive thing. And therefore, whatever we do to one ends up happening to the other. If we double the mass, we'll double the force. If we triple the mass, we'll triple the force. What we do to either of those variables will be directly reflected because they're directly proportional. But think for a moment, is the relationship between the force of gravity and the distance going to be directly or inversely proportional? And again, I'm hoping that you came up with the fact that they're inversely proportional because the radius, or the distance between them, as that increases, the force of gravity should go down. The further the things are away from each other, the less gravity they experience from one another. But it's actually not quite so simple because the relationship is not just with the distance, but with the distance squared. And so what I want to direct your attention to here is we can identify direct or inverse proportionality by using the equation. All right. So when I was comparing the force of gravity and the mass, I knew that they were directly proportional because as one increases, so does the other. But from the equation, they're both on opposite sides of the equal sign and on the same side of the fraction. So force of gravity is in the numerator, or the top of the fraction on the one side, and the masses are in the numerator, or top of the fraction on the other side. When they're on the same side of the fraction, but opposite sides of the equal sign, they're directly proportional. And when they're on opposite sides of the fraction and opposite sides of the equal sign, they're going to be inversely proportional. So since the force of gravity is in the numerator on the left and the radius is, or distance, is in the denominator on the right, then those are going to be inversely proportional. But since r is squared, we said that the relationship is with the distance squared, not just the distance. And so that complicates things a little bit because what's going to happen is if we were to double the distance, that's 2 times, but that 2's got to be squared now because the distance is squared in the equation. So 2 squared is 4, and I'm going to have an inverse relationship, so as one increases, the other decreases. So doubling the distance, I'm increasing that, and therefore the force would decrease by a magnitude of 4 because 2 squared is 4. So I'm going to have a quarter of the force. All right. And so we can do that really with any value. If I triple the distance between the two, 3 squared is 9, and therefore the force would be 1/9. If I did 5 times the distance, 5 squared is 25, so I'd have 1/25 the force. All right, and so that's a little bit challenging for students to put together sometimes, but if you just plug that value that you're multiplying by in and square it, it should sort of come out each time you do it. What we just were talking about is what's known as the inverse square law, and gravity is not the only thing that obeys it. All right, there's lots and lots of physical concepts that obey this, but we're focused on gravity now because we're trying to get into our astronomy unit. So the inverse square law simply states that the force of gravity, or whatever the other inverse square is going to be, between two objects changes in inverse proportion to the square of the distance between them. This is what we just went through. Okay, so inverse proportion just means that as distance increases, force decreases. They're opposites of each other. As one goes up, the other goes down. The square of the distance means that whatever the change in that distance is, I have to take that and square it. So for example, like we did a moment ago, if I were to take the distance between two objects and triple it, then the magnitude will be that 3. The magnitude of the change will be that 3 squared, so 3 squared is 9, and since it's inversely proportional, it's going to be 1/9 the original gravitational force. And so this is what we observe, this kind of graph right here, to demonstrate the inverse square law. You see that the y-axis represents the force, and the x-axis represents the distance. So as we double the distance, we get a quarter of the force that we started with. And as we triple the distance, we're down to 1/9 of the force that we had started with. And as we quadruple the distance, we're at 1/16 of the force that we started with. All of that is related to this square rule. So that is the end for us for Newton's law of gravitation. I hope this was helpful and that you can use this to complete the stations at the back of the room.